So for this unit, what we're going to be talking about is matter. Thinking back to prior courses, you might have an idea of what matter is. However, when we talk about matter in chemistry, we have to be a little bit more specific. So what exactly is matter? Well, matter is anything that has mass and occupies space. In science, when you're talking about matter, you can only talk about matter in the terms of mass, not weight. When you talk about in terms of weight, weight takes into account for gravity. However, mass does not. When we talk about matter, we have three phases of matter. In chemistry, we're going to look at solids, liquids, and gas. The first one is solid. Solid is defined as something that has definite shape and volume. As you look at a particle diagram, you can see that a solid is arranged nice and neatly with particles all touching one another. When we look at a liquid, liquid has a definite volume, but always takes the shape of the container. You can see that the particles are a little bit more spread out, not always touching one another, however they can be. Another thing to think about is that every state of matter has some type of movement. There's no such thing as a complete non-movement or no movement at all. So when you're looking at this, remember that even in a solid, a liquid, or a gas, particles are in constant motion, whether they're in a vibrational state of fluidity, or that of gas, which is a rapid motion. So again, liquid is a definite volume, but takes the shape of the container. Think of pouring water into a glass. Our last phase that we're going to talk about is a gas. Gas takes the shape of a container, has no definite shape, and no definite volume. Think of every time that you pour gas into a container, or a container itself always has gas inside of it, whether you can see it or not. Remember, these particles are moving around in rapid motion, and we're going to talk more about the motion of gases later on. So one of the things that we use to talk about gas in particular, or just molecules in general, is kinetic molecular theory. With a KMT, as is abbreviated, atoms and molecules are in constant motion. There's kinetic energy in any phase. We measure the average kinetic energy of these motions of these molecules and atoms, and we define it as temperature. The definition of temperature is your average kinetic energy. Again, as you can see, either whether you're a solid, a liquid, or a gas, you are in constant motion. So three phases of matter and how they relate to the kinetic molecular theory. The first is a solid. Particles do move, they're in a vibrational state, they're held tightly together, particles are very ordered, and they require the least amount of energy. Liquids. Some particle movement, they still are highly attracted to each other, particles are disordered, and they have a moderate amount of energy. And then finally, gas. Gases have lots of particle movement, very large distances between their particles. Particles are the most disordered, and they have the most amount of kinetic energy. So, big thing here is how can you change between phases? Well, honestly, all you have to do to change between the three phases of matter is either put energy in or take energy out of the system. Depending on how much energy you put in or out of the system, you're going to change phases. So when we look at this, we're going to look at the movement of particles and an input of or removal of energy. The first one, as you go from a solid to a liquid, that's defined as fusion and or melting. Now, as you go from a liquid to a gas, we define this as vaporization, or commonly known as evaporation. However, when you start going the other direction, when you take a gas and move it into a liquid, that's condensation, and a liquid to a solid is also known as freezing, solidification, or even sometimes crystallization. The easiest way to think about this is think about water. We've seen water in all three phases very commonly in our lifetime. Think about what happens to water as it goes from an ice cube to water, and then from water to a gas, or from a gas to water, and then from water to a solid. And remember, when we talk about water specifically, we think about it as a liquid. However, when we go straight from a solid to a gas, this is called sublimation, something that sublimes. Okay, you're changing straight from a solid to a gas. You really skip this middle step here as being a liquid. And then also you can go from a gas to a solid, which is known as deposition, to depose or to formate as a solid. So Looking at this, you need to know these two graphs moving in either direction, whether you're increasing your average kinetic energy or decreasing your average kinetic energy. So if you look at this bottom graph here, you can see that you're moving from a solid to a liquid to a gas. You can notice that there is a plateau at the melting point and a plateau also at the evaporation point. In reverse, this is also known as the condensation point and the freezing point. They are the exact same temperature. As you can see that the slope is 0, you can see that the temperature stays constant. At this first plateau, you have a mixing of solid and a liquid. At the second plateau, you have a mixture of a liquid and a gas. Until everything is uniformly at the same temperature, there is no reason or actually no rationale to why it would increase in temperature. Remember, everything in a system must be the same temperature until everything can increase. Temperature always goes from that of a high amount to a low amount. So until everything is the same temperature, energy will be transfused between those molecules. So looking at a heating curve. So looking at the heating curve or the cooling curve, you must know this curve in both directions. When we're looking at the heating curve and the cooling curve, it's very important to think about kinetic energy, but also potential energy. Potential energy is also known as positional energy because it's based off of the position of the molecules relative to one another. You can see that at each of the increases, your potential energy is staying constant, where your kinetic energy is increasing. However, at the plateaus, you can see that the potential energy is increasing. Think of the movement of those molecules. If you're a solid, you're close together. If you're liquid, you're moving farther apart. As the particles move farther apart, they're changing their position, thus increasing the potential energy. However, we know kinetic energy is constant because of our graph. Remember, another name for kinetic energy is temperature. The cooling graph or cooling curve is just the same as the heating curve, but in the opposite direction. You can see that as kinetic energy decreases, potential energy stays constant, and as kinetic energy stays constant, potential energy decreases. If you want to look a little bit more at this, this is a nice helpful hyperlink to look at heating curve and the movement of molecules. So one thing that we talked about is temperature measures the average kinetic energy of particles in a sample of matter. One thing you need to be fluent about is being able to convert between Kelvin and Celsius. This formula can be found on table T of your reference table. Key points on the temperature scale. Some of the things that we're going to start looking about and talking about is STP, standard temperature and pressure. Well, standard temperature is that of 273. 273 is also 0 degrees Celsius. The boiling point of water is 373 degrees Kelvin and also that of 100 degrees Celsius. What we call absolute zero, or the motion of no particle in space, is negative 273 degrees Celsius or 0 degree Kelvin. One interesting note to make is that for every degree Kelvin is the same degree change in Celsius. Therefore, the amount of energy to raise an item by 1 degree Celsius is the same to raise 1 degree Kelvin.